Alright, let's pick up where we left off on types of chemical reactions. Again, most of this is a quick review, but I want to make sure that you know all of the small little details. It'll help you get some extra points on your FRQ questions. First, the difference between a chemical reaction and a chemical equation. A chemical reaction transforms elements and compounds into new substances, whereas a balanced chemical equation just shows the relative amounts of reactants and products. I want you to pay careful attention to your phase symbols: solid, liquid, gas, and aqueous. If you're unfamiliar with aqueous or aqueous solutions, it is a solute that has been dissolved in water. No energy or time is ever alluded to with regard to the reaction itself. We don't see energy or how long it's taking. In a balanced chemical reaction, it just shows us how much and what do I have. Antoine Lavoisier, you may have heard his name last year, but he's the fellow responsible for law of conservation of mass. You should know this backwards and forwards. Matter can neither be created nor destroyed, and because of this concept, it means we have to balance equations. The number of atoms of a single element on the left is equal to the number of atoms of that same element on the right, even though it's been recombined with a different element. So I want you to jog your memory back to that one day in Chem 1 where I showed you a very quick little lesson using the Flintstones. We had Fred and Wilma, Barney and Betty. And we used them as an analogy to show the different types of basic reactions. Now, not all reactions are going to fall neatly into just one category, but I want you to be able to look at a reaction and tell me the type of reaction that's occurring. The first is synthesis. A synthesis reaction or composition reaction is when I have two or more simpler substances and they chemically combine to form a more complex substance. So in my little video, it was Fred plus Vilma go to the dance and they leave as a couple. General form, A plus B yields A, B. Over on the right hand side, our picture shows magnesium as single atoms, a nitrogen gas molecule, and then they recombine and form this magnesium nitride. Perhaps the most common synthesis reaction is when we combine hydrogen gas and oxygen gas to produce water, shown here on the right. And we need 2 hydrogen atoms for every 1 oxygen atom. They recombine, make these water molecules over on the right-hand side, and we need some kind of energy or spark in order to create that water. Next, we have decomposition reactions. Decomposition reactions are exactly the way they sound. It's the opposite of synthesis, so I have one complex substance that breaks down into more simple parts. So we're going to reverse that reaction. Fred and Wilma go to the dance as a couple, and then when they get there, they break up because Fred's a terrible dancer. The general form for decomposition reactions are AB yields A plus B. A common decomposition reaction is that of hydrogen peroxide. Hydrogen peroxide, or the formula for hydrogen peroxide, is H2O2. We are going to break that apart into 2 water molecules and 1 oxygen gas molecule. Again, I want you to jog your memory back to Chem 1. We did a lab in Chem 1 where we tested the amount of hydrogen peroxide found in a bottle. We know that it says 3%, but we wanted to test the validity of that statement and see if it actually was 3% or not. So if we know that hydrogen peroxide decomposes into water and oxygen gas, we can collect the oxygen gas that's being given off as a product and then use stoichiometry. If I have moles of oxygen gas released, I can determine the moles of hydrogen peroxide and then do mass percent to figure out how much hydrogen peroxide is in this solution. Because this bottle is a solution. It's not pure hydrogen peroxide. It's just a very tiny, tiny amount of hydrogen peroxide, and the rest is water. So let me jog your memory back, because it's always great to have as many labs under your belt as possible, especially for answering free response questions and working your way through them. In Chem 1, this lab, we had a ring stand, and on the ring stand we had a ring. Inside of the ring, what we did is, I'm going to use a different color here so you can see the difference. We put an inverted graduated cylinder. So our graduated cylinder was upside down. There's a base of the graduated cylinder, and there's a cylinder itself. And then we put that inverted graduated cylinder into a beaker that was filled with water. And so what we wanted to do, so here's the water. Our graduated cylinder was also filled with water, so this was where you filled your graduated cylinder with water, you put your hand on top of the open mouth of the graduated cylinder, you flipped it over and dunked it inside this beaker that also had water in it. So here's the graduated cylinder filled with water. This beaker is filled with water, and part one is done. The second part was the hydrogen peroxide itself. So over here in this other container, it had a stopper on it, and in our Erlenmeyer flask we added hydrogen peroxide, and we added a catalyst to that hydrogen peroxide so that it would decompose, or we added our solution of hydrogen peroxide from the bottle, and we added a catalyst for it to decompose very quickly. Our catalyst for this example was yeast. So we added yeast to the hydrogen peroxide, then we put the stopper on our container very quickly. Now that stopper had a hole in it, and out of the hole was a tube. We fished that tube into that beaker of water and into the mouth of the graduated cylinder. So as this hydrogen peroxide decomposes from this hydrogen peroxide into water and oxygen gas, those oxygen gas bubbles are going to travel through this tubing and into the graduated cylinder. So we know the laws of gas, and that gas exerts pressure on the water and pushes the water out of the graduated cylinder. So what we ended up having was a measurement of how much water was removed from this graduated cylinder, and I'm trying to erase and it's not working, but how much water was removed from the graduated cylinder and replaced by those gas bubbles. If I have a volume of gas bubbles, I can use that volume of gas bubbles and my ideal gas law. This was a pretty complex lab, but we can use the ideal gas law. If I collected 10 milliliters of oxygen bubbles, we had the pressure in the room was 1 atmosphere. Gas law, or not the gas law, the gas constant 0.0821 liter atmospheres per mole Kelvin, and the temperature in the room was probably somewhere around 25 degrees Celsius, which is about 293 Kelvin. We rearranged, we solved for a number of moles, and again using stoichiometry, because that's what this unit is all about, I used moles of oxygen gas collected and I converted it to moles of hydrogen peroxide. And last but not least, the question here says, why do we store hydrogen peroxide in a dark brown bottle? Well, recall that we needed a catalyst to speed up the decomposition of hydrogen peroxide in our lab. It is a quite slow process, so we store hydrogen peroxide in a brown bottle so that we keep the light out. Light is energy, and it works as a catalyst for the decomposition of hydrogen peroxide, and that's why you find it in a brown bottle. The next type of reaction that we had is a single replacement reaction. And here's where things got a little bit traumatic for you using that Flintstone example. In a single replacement reaction, a single uncombined element replaces another element within a compound. Single uncombined element replaces another element within a compound. In other words, one element trades places with another element in a compound. So here we have a single. I believe in the example, the single was Barney. And then our our couple was Fred and Wilma. So Barney goes to the dance by himself. Fred and Wilma go as a couple. And then after the dance, Barney and Wilma leave as a couple. And Fred is all alone, he's a single. So one element trades places with another element. Now what's important is that these elements that trade places have to have similar properties. So metals can only replace metals, metals replace metals, non-metals replace non-metals. And I'm not going to write the nonmetals bit because you already know that. One example of a single displacement reaction is when zinc metal replaces hydrogen and hydrochloric acid to yield zinc chloride and hydrogen gas. You did this in lab, also in Chemistry 1. You had a solid piece of zinc metal. Notice the state of matter, zinc is solid. You had some very potent hydrochloric acid. I believe it was 6 molar hydrochloric acid. It is the state of matter is AQ for aqueous because that hydrochloric acid has been dissolved in water. When the zinc was added to the hydrochloric acid, and zinc kind of has a black appearance, it just looks like a black crumbly rock. When you added the black zinc to the hydrochloric acid solution started to bubble right away, and that zinc started to decompose and break apart into small pieces. So you saw bubbles, lots and lots of bubbles being given off. That piece of zinc almost looked like it was rolling in the solution because it was bubbling so quickly and decomposing. So what happened in this reaction is that the zinc replaces the metal in the hydrochloric acid formula. I know that when I have metal plus nonmetal, the metal always comes first in a formula. So the hydrogen is my metal and the chlorine is the nonmetal. So because zinc is a metal, zinc will bump out the metal in my formula, which is a hydrogen. Hydrogen is a diatomic molecule, excuse me, meaning it only exists in pairs. So my products are zinc chloride and hydrogen gas. Notice a little 2 on the hydrogen because hydrogen is diatomic. If you happen to see this extra arrow here at the end, that simply means that a gas is given off and it's being released as bubbles. Double replacement chemical reactions. In a double replacement reaction, the anions and cations of 2 compounds switch places and form 2 entirely different compounds. And this was the most dramatic slide on our lesson last year, where we had 2 couples go to the dance, and then they switch partners and leave the dance 2 brand new couples. So we had Fred and Wilma go to the dance together. We had Barney and Betty go to the dance together. And then after the dance was over, Fred left with Betty, Barney left with Wilma. Very traumatic, I know. Shouldn't have used cartoons, but it was the best way for me to use an analogy for you. In general form, this reaction is AB plus CD yields AD plus CB. In this general form, A is a metal, and B is my nonmetal. C is a metal, D is a nonmetal. So when they recombine, they're going to recombine in those same sets. The metal will replace the other metal, nonmetal will replace nonmetal. So here, my A is going to be replaced by the metal in this couple over here, which is the C. And notice over here on this end, I have CB as my product. So anions are negatively charged ions. Cations are positively charged ions. Your cations are metals, are nonmetals. Lead 2 nitrate. This 2 tells me the oxidation number of lead, since lead is a transition metal, and transition metals have more than 1 oxidation number. So that Roman numeral tells me that lead has a +2 charge. Nitrate has a -1 charge. So when I drop and swap, check out my formula. Here's my lead. It gets the 1 from nitrate, and my nitrate gets the 2 from my lead. Drop and swap. So lead nitrate, it's an aqueous solution. I also want you to pay careful attention to your states of matter. I'm starting out with 2 aqueous solutions, meaning these 2 salts were dissolved in water. Then they were combined together. As a result, I get a solid and an aqueous solution. So anytime I have 2 solutions that are mixed and I get a solid as a product, we call this a precipitate. I would encourage you to write this word down. It seems like lots of students forget the term precipitate from Chem 1 to Chem 2. A solid that forms when 2 aqueous solutions are combined. Now, not all double replacement reactions are going to result in a solid being formed, so I want you to pay careful attention to those states of matter before and after. If you are forming a solid as a product, I can almost guarantee that you're going to be answering questions about that solid, or using that solid as reasoning or explanation for part of an FRQ. Next up, we have combustion reactions. These are fun. We get to burn. A combustion reaction involves a reaction between any combustible material and an oxidizer. The most common oxidizer is going to be oxygen, and that's really the only oxidizer that we used last year. And I did give you a little white lie last year, and I said that the products of all combustion reactions are carbon dioxide and water, and that is not necessarily true. Now, when you burn something like these fuels, and that's what we looked at, these hydrocarbons in Chem 1, so you have fuels like methane, CH4, and octane, H18, all of these fuels are hydrocarbons. So when they are combusted, they're going to form, these are the products. The products of a combustion reaction are simply the oxides of that which is combusted. So if I take this carbon and hydrogen, or this hydrocarbon, the oxide of carbon would be carbon dioxide, and the oxide of hydrogen would be water, and those are my products. So let's look at a combustion reaction that does not include a hydrocarbon, like magnesium. And we also did this reaction last year as well. We actually, or in Chem 1, you did it more than once. I gave you a piece of magnesium ribbon, and I had you burn it. That magnesium ribbon, it's just a very small, shiny silver piece of metal. And as soon as you put it into the flame, it turns a very, very, very bright white. It was maybe one of the first things you set on fire in Chem 1, and I think a lot of groups got really scared when they did this lab because they didn't know that was supposed to happen. But what you saw there, what you experienced, was a combustion reaction. So how would we write the combustion of the magnesium ribbon? Magnesium, solid metal, plus oxygen. Oxygen is my oxidizer. If I were to write those two products, carbon dioxide and water, like I previously told you, which was a fib, law of conservation of mass, I have carbon here, but there's no carbon over on the left side that I can balance. So this can't be right. Now, by definition, a combustion reaction is going to produce oxides of that which is combusted. So if I combust magnesium, the oxide of magnesium would be none other than magnesium oxide. So the correct chemical formula for the oxide of magnesium would be MgO. Magnesium is a group 2 metal and has an oxidation number of +2. Oxygen has an oxidation, so when I drop and swap, my subscripts cancel. Additionally, most folks think of combustion in the literal burning sense, which is true but not wholeheartedly, because cellular respiration, which you learned about in biology, is one of the most famous combustion reactions, and you're not setting little fires inside your body every time you break down sugar in your digestive system or in your cells. That would be crazy. But let's look at our formula. So we have glucose here on the left as a reactant. I'm adding 6 oxygen molecules. Anytime I've got that oxygen there on its own, I know my oxygen is the oxidizer. The oxides of this glucose molecule are going to be carbon dioxide and water. So the carbon forms, sorry, my arrows got a little crazy there. My carbon, the oxide of carbon is CO2. The oxide of hydrogen is H2O. And of course, tons of energy is released. That's the energy that you and I use to get on and about our day. All right, flip the page. And now let's take a closer look at those precipitates from our double replacement reaction from before. If you really want to know a little bit more about cellular respiration, if you're intrigued by the process, you can read the information up here. I'm going to skip past it for now to save us a little bit of time. So let's look at our precipitation chemical reactions and some of the information that we can use and how we can apply it to stoichiometry. The formation of a precipitate is a driving force for a chemical reaction. And here's your official definition. A precipitate is an insoluble solid that is formed when two aqueous solutions are mixed. So we essentially said that on the previous page, but now we're reiterating it. It's the second time you've heard it. You're probably going to be tested over it. We then often separate that precipitate from the solution by filtration, and then we use a process called gravimetric analysis. So let's definitely either underline or highlight this information. We separate the precipitate using a filtration system, and then once we have that solid removed from our solution, we can do a gravimetric analysis. And this probably is sounding a little bit familiar because it was question 2 on your quiz last week. Let me just remind you about that question. In the second experiment, a student is given 2.94 grams of a mixture containing anhydrous magnesium chloride and potassium nitrate. To determine the percentage by mass of magnesium chloride in the mixture, the student uses excess silver nitrate to precipitate the chloride ion as silver chloride. Starting with 2.94 grams of sample dissolved in water, briefly describe the steps necessary to determine the mass of the precipitate. So what am I going to have to do if I have these two salts? I've formed aqueous solutions out of them, and I want to analyze that sample. It says that we're going to form a precipitate sodium chloride. So I'm going to mix the solutions together. I'm going to form this precipitate silver chloride, and then I need to remove that precipitate using some kind of filtration. A funnel and filter paper will work just fine. After you've removed the solid, we have to rinse it to make sure there's not excess solution left over. Then we have to dry it, so put it under low heat until that salt is completely dry. And then I can use the mass of that solid that I've recovered from solution to solve a multitude of stoichiometry questions. We call that gravimetric analysis, where I use a mass of a solid that I've removed from a solution, that precipitate. I'm going to use that mass to calculate another desired amount. Now, I haven't talked about the picture yet, but I'm going to skip past it for now, and then we're going to come back to it in just a moment. So let's move that a little bit higher. To identify the precipitate, you have to know your solubility rules. Now, there are a very long list and kind of complicated versions of solubility rules, so we're going to keep it pretty simple. Solubility rule number 1. All nitrates are soluble. Nitrate, if you have forgotten, nitrate, the formula is NO3 with a -1 charge. So if a formula has a nitrate at the end, it is soluble. It dissolves. Rule number 2. All group 1 metals and ammonium salts are soluble. So if you check on your periodic table, any formula that has a group 1 metal, a metal with a +1 charge, or ammonium, because ammonia has a +1 charge as well, because they have a group 1 or +1 oxidation number, they're highly reactive, which means it doesn't take very much energy to dissolve that salt. The attraction between the water molecules and the ions is very easy, so they dissolve very readily. All you need to know is that group 1 metals and ammonium salts are soluble. So ammonia plus any non-metal, chlorine. Ammonium chloride is a soluble salt. Sodium, group 1 metal, chloride is a soluble salt. Rule number 3. Halides. All are soluble except the heavy metal bad guys, silver, mercury, or lead. So your halides are those group 7, fluorine, chlorine, bromine, iodine. Those are your halides. They're all soluble except for these heavy metals. So if I have silver, mercury, or lead, silver, Ag, mercury, Hg, or lead, Pb, if I have any of these metals combined with your halides, so in your quiz on your quiz last week, silver combined with that halide chlorine, insoluble. It does not dissolve. It forms a precipitate in solution. If I have lead chloride, also insoluble, doesn't dissolve. So again, those halides are those group 7 nonmetals. Rule number 4, your strong acids are all soluble. Hydrochloric acid, hydrobromic, hydroiodic, nitric, perchloric, and sulfuric. All of these acids are strong, meaning that they dissociate readily. They very, very easily separate into ions as opposed to staying as molecules. That's their definition. So your strong acids, you're going to write them as ions in solution as opposed to the molecules. So you'll write them as these ions, H plus and Cl minus, as opposed to HCl, anytime we're writing a dissociation reaction. And last are your strong bases. So your strong bases are any hydroxide. Hydroxide is OH. Any hydroxide that's bonded with a group 1 or group 2 metal is considered strong. So when we write these bases, or when we say a strong base, it means it dissociates readily. That instead of existing as, let's choose a group 1 metal, group 1, how about potassium? So instead of existing as potassium hydroxide, if I add water to potassium hydroxide, it will dissociate and form potassium ions and hydroxide ions. It won't exist as KOH, it will exist as K plus ions and OH minus ions. By definition, they are very, very soluble. So now let's take a look at that picture from before, and let's see if we can figure out what's going on. We have, in this beaker over on the left, it looks like we have, let's look at our key over here. Oops. Let's look at our key. We have in solution, and I can tell it's a solution because I can see this ring up here at the top, so I know it's liquid. I have potassium ions in pink. I have barium 2 plus ions in purple. I have the nitrate ions and chromate ions. Once they're all combined, over on the right-hand side, oops, my arrow won't work. Over on the right-hand side, I still have potassium ions. I still have these nitrate ions because by definition, these nitrate ions are soluble. Group 1 metals are soluble. But then I have this chromate down here. Chromate is insoluble, and it's not one of the rules that you essentially have to memorize. I would roll with the rules that you see down below. But barium chromate, this BaCrO4 is insoluble, and notice they form this solid. You see that they're chemically combined at the bottom. So we're going to take that mass of the barium chromate, we're going to isolate it. Here's the actual picture on the far right. So I see the liquid solution left at the top. Floating around in that liquid solution are going to be potassium ions and nitrate ions, a whole bunch of them. Oop, that should be an N, kind of looks like an H. So there's all of these ions floating around, and my barium chromate has now formed this yellowish solid that's sitting at the bottom of the container. I'm going to filter that yellow solid out. I'm going to use the mass of that barium chromate to solve a multitude of questions. So let's put our solubility rules to the test. And I know the answers are already there at the bottom of exercise 8, but we're going to go through some of these together. Let's look at exercise A. Using the solubility rules, predict what will happen when the following pairs of solutions are mixed. So one thing I want you to be able to do is picture what's happening in the container on the molecular level. So I'm going to take potassium nitrate solution and I'm going to dump it into this container. So now I have liquid in my container, and I have potassium ions and nitrate ions floating around. And I'm only drawing one of each, but there are millions upon millions of these ions all floating around. I also have barium chloride. I'm also going to take that solution of barium chloride and I'm going to add it to this one beaker. So now I have barium ions. Barium has a +2 oxidation number, and chloride ions also floating around in solution. So I want to know what happens when these sets of ions come in contact with one with another. I know that potassium nitrate and barium chloride on their own are soluble. I can easily dissolve those, and I know they're soluble because I see this AQ next to the formula, so I know that they've been dissolved in solution. If I can circle that, there we go. So I want to know what happens when these two pairs meet. So now what happens when the K and the Cl meet. What happens when barium and nitrate meet? Is potassium chloride soluble or insoluble? Is barium nitrate soluble or insoluble? And what do those formulas look like? So, I can't move that guy, so I guess I'm just going to have to erase him for now, or get rid of him. Oops. There we go. Maybe? There we go. So now let's rewrite our chemical reaction. Potassium nitrate and for my double replacement, another technique that we used was inside-outside. My insides form a new compound and my outsides form a new compound. So my insides, barium, has a +2 oxidation number, and the nitrate has a -1 oxidation number. If you don't know your polyatomic ions, you better get on it. Drop and swap. So my nitrate gets a 2. It's a 2. And my outsides are potassium +1, chlorine -1. Drop and swap, that formula remains the same. So now let's look at our two products. Barium nitrate. What do I know about nitrates? Rule number 1 said that all nitrates are soluble, so barium nitrate gets a little AQ, it's aqueous. Potassium chloride. Chloride is a halide. It said all halides are soluble except for those heavy metals. I also know that potassium is a group 1 metal, and all group 1 metals are highly soluble. So potassium chloride is also an aqueous solution. So in my container, remember the one I drew right before, I erased it now, but in my container I had all ions floating around. Well, they would all remain as ions floating around in solution. So our answer is all of the ions remain dissolved in solution, no chemical reaction occurs. Let's try example number 2. So I'll give you a second to copy that down while I try to get rid of it. Maybe I'll be more successful this time around. There we go. And let's look at example number 2. I have sodium sulfate and lead nitrate. So again, I'm taking these aqueous solutions, I'm dumping them all in one container. And I have sodium ions, I have sulfate ions, that's a 2. I have lead +2 and nitrate -1. So I've got these ions floating around in solution. What happens when my anions and cations switch partners? So now my sodium will combine with the nitrate, and the lead will combine with the sulfate. So if I rewrite, envision there's a plus there instead of the word and. If I rewrite, I will have sodium +1 charge. It recombines with the nitrate. Sodium +1, nitrate -1. My formula is done. And my second product is that lead. I know lead has a +2 oxidation number because of the formula. So let me write that one down here. Because it was lead nitrate. I'm going to look at the subscripts on my formula, and I'm going to unswap to figure out what the oxidation number is for lead. Remember, lead is a transition metal, so I have to use either the chemical formula or the Roman numeral that's in front of it to figure out what its oxidation number is. If I don't see a subscript in the formula, it means that there's a 1 there. So if I unswap, my 1 will go here, the 2 will go there, and I know the positive cation always goes first, so there's plus, and the negative ion goes second, there's a minus, so my lead has an oxidation number +2. But back to our new product, lead is going to combine with sulfate. Sulfate has an oxidation number of -2. When I drop and swap to get my new formula, my subscripts cancel. So now we need to look at our products and see if they are soluble or insoluble. Let's first look at this formula here, sodium nitrate. First of all, I have a group 1 metal. If it's a group 1 metal, it's soluble, it dissolves. I also see nitrate. Nitrates are all soluble. So this is an aqueous. This will remain as ions in solution. Then I have lead sulfate. Rule of thumb, if you see lead as part of your product, it's going to be a precipitate. I know this wasn't one of the rules on the previous page, but it is on the solubility rule sheet that I gave you over the summer. Sulfates are insoluble. So this lead sulfate is going to form a solid in solution. So when they recombine, let me redraw this, this beaker. So when I draw my beaker again, here's my beaker, because you will be asked not only to draw and write about what's happened in the reaction, but what it looks like afterwards. So there's my liquid, and I'm going to have sodium ions, Na+. I'm going to have nitrate ions, NO3-, and then at the bottom, I'm going to have this little mound, this solid, and that solid is going to be lead sulfate. I'm not going to do example C. I think you guys kind of get the drift. It's all about learning those solubility rules and then being able to draw what you see afterwards. Also recombining those elements and forming the correct chemical formulas. So great news, we can describe reactions in aqueous solution in 3 different ways. So just to reiterate, an aqueous solution is a solute that has been dissolved in water. So I have positive and negative ions floating around with water molecules. So in this beaker that I drew up here earlier, I have these nitrate ions and sodium ions. And one thing I left off, but should be kind of in the background here, where we should know that they're floating around as well, are water molecules. The water molecules are what separate the ions one from another. You don't have to draw them in your picture, but you should know that they're there. So there are 3 different ways that we can write down what's going on in solution. Option number 1, which is what we did all in first year chemistry, we write a complete balanced equation. It gives us the overall reaction stoichiometry, which is great if we're doing that gravimetric analysis, what we did in part 2 of your stoichiometry free response quiz last week. But there's one problem. And this is kind of a huge problem because you're expected to know this in AP. It doesn't show you the forms of the reactants and products as they exist in solution. So if you go back up and look at what we did in exercise number 8, on the product side, we put aqueous or solid, depending on what type of solubility those products had, but it doesn't necessarily show us how they exist in that solution. That's why I did the drawings for you, so you could see how they exist in solution. The second option that we have is called a complete ionic equation. So here we represent all reactants and products that are strong electrolytes as ions. An electrolyte meaning they completely dissolve and they are going to conduct high volumes of electricity. So instead of writing an aqueous solution as, say, KNO3, instead of writing it that way, I would write this as K plus NO3-. So this tells me that these exist as ions in solution. They're not actually chemically bonded together. They've been separated by water molecules. So I would write all reactants and all products in their ionic form. Option number 3 is called a net ionic equation. And this is what you'll be looking for, or you'll be asked to do on the AP exam. This not only includes the solution component, this only includes the solution components that are undergoing a change. So if I started out with potassium ions to start, and I know potassium ions are highly soluble, so on the product side they also look like K+ ions, there was no change in the potassium. It stayed as ions in solution. We would call those spectator ions. They're not included in the net ionic equation. The only things that we do write are those that change forms. So if I go back up real quick, an example B up here. In example B, we ended up with lead sulfate as a product. So if I were to write the net ionic form of this equation, let's see if I can get rid of some of this stuff. So if I were to write my net ionic equation for that lead sulfate, I would just have the lead ions and the sulfate ions, and on the other side PbSO4 solid. The other ions remain as ions in solution. The sodium, the sodium and the nitrate. They're highly soluble. They don't change at all from reactant to product side, so I'm going to leave them off. Very important when you're writing your net ionic equations that there's always a conservation of mass and charge. Mass and charge. Ooh, meant to highlight that. Mass and charge. So let's take a look at exercise number 9 and see if we can't complete one together. For each of the following reactions, write the molecular equation, the complete ionic equation, and the net ionic equation. So let's look at example A. Aqueous potassium chloride. Potassium is a K with a +1 oxidation number. Chloride is Cl, -1 oxidation number. My formula is complete. It's aqueous, so I'm going to put AQ. It's added to aqueous silver nitrate plus silver, and anytime you see silver, you should already kind of have a note in your head, hey, if I see silver, it's one of those heavy metals. It is probably not going to dissolve. Silver has a molar mass of 107.87. That's pretty heavy. So silver chloride, and it doesn't say silver 2 or silver 3 chloride, so because it doesn't have a number, I know that the oxidation number for silver here is +1. If the oxidation number for silver was anything other than 1, I would see it in Roman numeral form here in between the silver and the nitrate in the word formula. But nonetheless, silver +1. Nitrate, NO3, -1 charge. Drop and swap, my formula is complete. Is aqueous. And now I'm going to recombine. So remember, if it's aqueous, these exist as ions in solution. To recombine, I'm going to do my insides and my outsides. So my insides are silver chloride +1, chloride -1. Halides, we said, were soluble unless they're paired with a heavy metal. Silver is a heavy metal, so I get a solid. And my second product, my outsides, potassium nitrate, KNO3. There's a +1 and a -1. My formula is complete. Group 1 metal, soluble, always soluble, so really it doesn't even matter what I have here. But I also have nitrate, which is highly soluble, so I know that KNO3, without a doubt in my mind, is going to be an aqueous solution, AQ. The next task is to write this same reaction, but in ionic form. And this is complete ionic form. So we're writing down all of the ions. And I'm going to do this down below. So I have potassium ions, and they're AQ, aqueous in solution, plus chloride ions, plus silver ions, Ag, plus nitrate ions. And then over on my product side, I know that the silver chloride forms that solid, so AgCl solid. And I still have potassium ions and nitrate ions, I'm out of space there. And both of those ions are in the aqueous form. I don't have a ton of space, but those have an AQ next to them. Now, all that writing seems like kind of a waste to me. So what we want to do, or what's most important, the most important skill, is to be able to write the net ionic equation. Notice that my potassium before and potassium after is exactly the same. My nitrate before and after is exactly the same. So why include them at all if they're just spectating? They're not part of the reaction itself. So we're going to get rid of them and write our net ionic equation. So we have the chloride ion from this potassium chloride that's going to react. It's in aqueous form, plus the silver ion from the silver nitrate, also in aqueous form, and they create silver chloride, a solid. So net ionic equations, much simpler, a lot less writing. It includes only those ions that are changing, that undergo a change in a precipitation reaction. The answer to example B is noted down below. I would recommend that you try example B on your own and then check yourself and see how well you've done. So now back to that whole gravimetric analysis business. If we do a chemical analysis of mixtures by isolating that precipitate, we call it a gravimetric analysis. So here are your steps. You mix the starting chemicals to form that insoluble salt or that precipitate. You filter out the precipitate, that new salt that's insoluble. You dry it to a constant mass. That was, I believe, part A of that quiz. How does the student know that it was sufficiently dry? And it's because the mass stayed constant or relatively constant. And then once I have the dry mass, I can put it on a scale to figure out how much it weighs, and I can use that with my stoichiometry to determine any desired quantity in that balanced chemical equation. Exercise 10. Calculate the mass of solid sodium chloride. I know I'm searching for grams there. That must be added to 1.50 liters of a 0.1 molar silver nitrate solution to precipitate all of the silver ions in the form of silver chloride. Very first step, before I can solve for anything, I need to write a balanced chemical reaction, and I'm going to encourage you to draw what would be happening in this container when these things were added together. In our reading, it tells us that we have solid sodium chloride So let's talk about our picture. Here's my container. It is 1.50 liters in volume, and it contains a 0.1 molar solution of the silver nitrate. So if it's a solution, it exists as ions. So I have silver ions and nitrate ions floating around in solution. Then we need to add this mass of solid sodium chloride. So when I add the sodium chloride, it's a solid, so they're going to look like these big dots. There's my sodium chloride as a solid. When I add that solid mass, what does it look like afterwards? Well, now I have all of these sodium ions and chloride ions. I only drew one of each, but in actuality there are tons and tons of them. Now I have these ions floating around in solution. I know that when these two ions come into contact, that silver plus and the chloride minus, they form that solid precipitate silver chloride. The sodium ions and the nitrate ions remain as ions in solution, and I'm done. Now back to the question at hand. What is the mass of that salt that I need to add to completely remove all of these silver ions? That's what it's saying. I want to get rid of all of these silver ions, so essentially how many chloride ions do I need to add to this solution in order to get rid of them? Well, in order to know how many chloride ions I need to add, I have to know how many silver ions are already sitting there in solution. I have a solution that's has a volume of 1.50 liters, and its concentration moles per liter, its concentration is 0.100 moles per liter. I've just rewritten that big M, that concentration is moles per liter. If you consider the formula of silver nitrate, I'm going to write it down here. If I look at my formula, how many moles of silver ions are there in 1 mole of silver nitrate? Look at your subscripts. I don't see 1, so that means it's 1. So 0.100 molar silver nitrate is the same as 0.100 molar silver ions. Let's say, for example, and I know it's not the correct formula, but let's say, for example, that silver had a subscript of 2 in this formula. That means that when it dissociates, it releases 2 silver ions for every 1 nitrate ion. So its concentration in my solution, 0.100 molar, I'd actually have to multiply it by 2 to get the concentration of silver ions, since it releases 2 for every 1 nitrate. But that's just in case you see that in a different problem. All right, back to the task at hand. We need to calculate the mass of solid sodium chloride. I need grams of sodium chloride that must be added to 1.5 liters of a 0.1 molar silver nitrate solution. So hopefully you've remembered that if I take that volume, 1.50 liters, and I multiply it by concentration, which is moles per liter, 0.100 moles per liter, my liters cancel and I'll be left with moles of silver nitrate. So I need to convert these moles of silver nitrate to grams of sodium chloride. Now, one thing that I haven't mentioned, because this chemical reaction, it's all a 1-to-1 ratio, we do need to make sure that we have a balanced chemical equation. Here, everybody is 1s. You may not always get 1s as coefficients, but you'll want to check ahead of time before you start your stoichiometry. So let's start this problem with that 1.50 liters of silver nitrate. And let's try to put it all in one nice neat problem. 5 liters of silver nitrate on the top. I need liters of silver nitrate on the bottom. Liters, AgNO3. And I have liters of silver nitrate and my concentration here. So 0.100 moles of silver nitrate per liter of silver nitrate. That's 1 liter. Next step, I need to get rid of my moles of silver nitrate and convert them to grams of silver chloride. So I'm going to put my mole of silver nitrate here, and I need to convert that to moles of sodium chloride. And it looks like I have a 1-to-1 ratio for every 1. And last but not least, this particular question asks me for mass of sodium chloride. So I need to get rid of this mole of sodium chloride and convert that to grams of sodium chloride. Molar mass of sodium chloride. Sodium has a molar mass of 22.99. Chlorine has a molar mass of 35.45. Add those together. The molar mass of sodium chloride is 58.44 grams for every 1 mole. Complete your little railroad there. Multiply across the top. Divide by everything you see at the bottom. We need how many significant figures? 1, 2, 3 significant figures there. 3 significant figures there, so we need 3 significant figures in our answer, and we should get 8.77 grams sodium chloride. Put a box around your final answer, and hooray, done. Exercise 11. When aqueous solutions of sodium sulfate and lead nitrate are mixed, sodium sulfate precipitates. Calculate the mass of lead sulfate formed when 1.25 liters of 0.05 molar lead nitrate and 2 liters of 0.0250 molar sodium sulfate are mixed? Well, this question isn't as nice, but we need to start with a balanced chemical reaction. So we have sodium sulfate, and it's an sodium nitrate. Sodium is a group 1 metal, it's soluble. Nitrates, also soluble. All right, next step. It says calculate the mass of lead sulfate formed. So I need to calculate mass of this. Let's make sure that we have a balanced chemical equation. I have 2 sodium on the left. I need 2 sodium on the right. 1 sulfate on the left, 1 sulfate on the right. 1 lead, 2 nitrates, 2 nitrates. All right, now we're balanced. Now let's fill in our starting amounts. So we have 1 container, and in that container we are adding 1.25 liters of this 0.05 molar lead nitrate. Sorry, it's not cooperating with me. So we've added 1.25 liters of lead nitrate and 2 liters of 0.25 molar sodium sulfate. So in this container now, after I've added everybody, I have a total of 2.25 liters. Not 2.25, 3.25 liters. The 1.25 liters of the lead nitrate and the 2 liters of the sodium sulfate. So my total volume here is 3.25 liters. In this container, I have sodium ions, I have sulfate ions, 2 minus, I have lead ions, and nitrate ions. So what I need to determine next is the mass of this sodium sulfate that's going to form. I know it's an insoluble compound, so I need to know how much I'm going to make. And before I can do that, I need to figure out which one of these 2 solutions is my limiting reactant. Which one do I have less of? I'm going to do a quick comparison because there's a 1-to-1 ratio for both of my aqueous solutions. I'm simply going to figure out how many moles I have of each one, and the one with the fewest number of moles is going to be my limiting reactant. So let's multiply our volume times concentration of each one of our reactants to determine the total number of moles. If we start with that sodium sulfate and we take the 2 liters and multiply it by its concentration of 0.025 molar, you should get a total of 0.05 moles of sodium sulfate. I'm going to give you a second. I want you to do the same thing for the lead nitrate while I get mine up on the board, and we're going to compare number of moles. All right, did you get 0.0625 moles of lead nitrate? Let's compare. Let's figure out who's the limiting reactant. Remember, for every 1 mole of sodium nitrate, I need 1 mole of lead nitrate. So if I compare their number of moles, I see here that the number of moles of the sodium sulfate is less, so that means it's my limiting reactant. I'm going to start my stoichiometry problem with the 0.0500 moles of sodium sulfate. So now that we have our limiting reactant, let's use some stoichiometry and let's convert that to grams of lead sulfate. To get rid of my moles of sodium sulfate, I'm going to use my molar ratio. It is a 1-to-1 ratio. For every 1 mole of sodium sulfate, Na2SO4, I create 1 mole of lead sulfate. And we need grams of lead sulfate, so we are going to use our molar mass of lead sulfate. 1 mole of lead sulfate has a molar mass of 303.27 grams. Multiply across the top, divide by everything you see at the bottom, and we need how many significant figures? Look at your original measurements. It looks like we need 3 significant figures. Everybody has 3 going across. Our answer is 15.2 grams of lead sulfate. Put a box around your final answer, and we are finished.